Take anything, cut it in half, then in half again. Keep going forever. Your mind says you can. The universe says you stop. There is a size so small that space itself falls apart, where a ruler turns into a black hole, where time runs out of ticks, and heat climbs to a temperature nothing survives. It is called the Planck scale, the floor of reality. If the smallest thing that exists sounds worth cracking open, a quick like or subscribe helps. Now hold on tight. We begin. Pick up a square of chocolate, snap it in half. Now snap that half in half. Do it again. Your fingers get clumsy fast, but your imagination never does. In your head, you can keep splitting forever, smaller and smaller, with no end. That feeling is one of the oldest ideas humans have ever had, and it is wrong. More than 2,000 years ago, a Greek thinker named Democritus sat with the same feeling. He guessed that if you kept cutting, you would reach a piece so small it could split no further. He called it the atom, a word that means uncuttable. He had no proof. He had only a hunch about the bottom of the world. For centuries, that hunch looked right. Scientists found atoms, tiny, countless, the building blocks of everything you can touch. Case closed. Then someone looked closer. The atom cracked open. Inside sat a dense little core, the nucleus, with a cloud of electrons whirling around it. So the uncuttable thing had parts. Then the nucleus cracked too. Inside hid protons and neutrons. And when physicists pushed harder, those split into even smaller specks called quarks. Every time we thought we had hit the floor turned into another door. So here is the question that should keep you up tonight. Does it ever stop? Is there a real bottom to reality? A smallest possible size? A final door with nothing behind it? Or does the splitting run on forever? Worlds, inside worlds, all the way down. For most of history, that question felt like a fairy tale. You could argue about it at dinner, but you could never test it. Then, near the end of the 1800s, physics shifted. A quiet, careful scientist did some arithmetic that had nothing to do with cutting things in half. He was trying to invent a cleaner way to measure the universe. And by accident, buried in his numbers, he found a size chosen by the laws of nature themselves, a length so small that our biggest words for tiny cannot reach it. Below this size, according to our best physics, the very idea of distance breaks apart. Space stops behaving like space. Down there, asking how far becomes as meaningless as asking what color the number 7 is. This smallest step has a name, the Planck length. It is the real answer to the chocolate bar. You cannot split forever. Somewhere far below the atom, far below the quark, the universe throws up a wall so strange that trying to peek past it, as you will see, does something no wall has any business doing. We reach that wall by the end of this journey. But the story of how we found it begins with a man who had no idea he stood near the edge of reality. He was busy being annoyed by rulers and clocks. Every country measured things its own way, with feet based on old kings and hours based on the spin of the earth. He wanted numbers that owed nothing to human bodies or human planets. He wanted numbers an alien on the far side of the galaxy would understand without a single word of explanation. And in chasing that simple dream, he tripped over the smallest thing that exists. The scientist's name was Max Planck. In 1899, he was a serious, buttoned-up German physicist with a bushy mustache and a love of order. He was not yet famous. The great quantum revolution he would help start was still a year away. On this particular day, he was wrestling with a small, nagging problem. Every ruler on Earth is a human invention. Look at it this way. A foot was once the length of a king's foot. A meter got carved from a metal bar locked in a vault in Paris. A second came from slicing up the day, and the day comes from how fast our planet happens to spin. Every unit we use is an accident of history, tied to human bodies and one particular world circling one particular star. That bothered Planck deeply. He asked a beautiful question. What if you threw all of that away? What if you built your measurements only from the deepest laws of nature, the numbers that stay the same everywhere in the cosmos? Nature hands us a few of these numbers for free. They are called constants, and they never change. One is the speed of light, the fastest anything can travel. Another is the strength of gravity, how hard mass pulls on mass. A third is a strange little number from the newborn world of the quantum, which controls how tiny things behave. Planck took these fixed numbers and started combining them. He multiplied and divided, twisting them together like puzzle pieces, hunting for a way to spit out a pure length using nothing but the universe's own rulebook. And the pieces fit. Out popped a number with the units of distance. A length built from light, gravity, and the quantum, with no human fingerprints on it anywhere. He did the same trick for time, and for mass, and for temperature. Each one came from the same fixed constants. Each one belonged to the universe rather than to us. He had invented what we now call natural units. And Planck loved the idea for a lovely reason. These units would be truly universal. Picture an alien civilization 10,000 light years away. They have never met us. They will never see our metal bars in Paris or care how fast our planet spins. But they know the speed of light, because light is the same for everyone. They know the pull of gravity and the rules of the quantum, because those rules run the whole cosmos. So, if they build their measurements the way Planck did, they will land on exactly the same length he did. It is the closest thing to a truly cosmic ruler, a measurement any mind anywhere would discover. Planck was proud of the elegance. But here is the strange part. He had no idea what his little length actually meant. To him, it was a tidy mathematical curiosity, a clean way to write physics. He never guessed that he had stumbled onto a boundary. He could not have guessed, because the physics that gives this number its terrifying meaning would not be invented for another 20 years. The number just sat there in his notebook, quiet and harmless, waiting, a string of zeros followed by a 1. And when scientists finally understood how small it truly was, and what happens to anything foolish enough to approach it, the harmless little number would become the most important wall in all of science. Just how small are we talking about? Small enough to break your brain. Get ready, because this is the moment the size of the Planck length stops being an idea and becomes a punch in the gut. Let me build it up slowly so you feel each step. Start with something you know. A single human hair is about as thin as everyday things get. Now zoom into that hair until a single atom fills your view. An atom is so small that millions of them line up across the width of that hair. You have already left the world your eyes can see. Keep going. Dive inside the atom, past the electron cloud, down to the nucleus at its heart. The nucleus is tens of thousands of times smaller than the whole atom. And inside the nucleus sits a single proton, one of the specks that make up the core of matter. We are now deep in a realm no microscope on Earth can show you directly. Surely we have reached the bottom. We have not even come close. Take that proton, now shrink down until the proton looks as big as an entire city. Keep shrinking. The Planck length, next to a proton, is smaller than that proton is next to the whole city. Here is the number that says it plainly. A proton is about 100 billion Planck lengths across. Read that again slowly. 100 billion. Written out. That is a 1 with 20 zeros trailing behind it. You would have to lay that many Planck lengths side by side just to stretch across a single proton. And a proton is already so small that 100 million of them would barely span the period at the end of this sentence. There is no honest picture for this. Every comparison falls short. If you blew up a single atom until it was as wide as the entire Earth, the Planck length inside it would still be smaller than a grain of sand. If you blew up that same atom to the size of the whole galaxy, the Planck length would finally grow to something you could almost imagine holding. That is the scale we are dealing with. This is the smallest length that appears anywhere in physics. the point our best theories name as the likely bottom of space itself. Everything you have ever seen, every atom in every star, in every galaxy, is built on a stage whose smallest possible tile is this unthinkably tiny step. And now the questions start to bite. If this length is real, what lives down there? What does the universe look like at the very bottom, in a place so small that a proton feels like a continent? Does space stay smooth all the way down, like a perfect sheet of glass? Or does something happen to it, something wild, when you get close to the final tile? For a long time, nobody could even guess. The number was just a curiosity in a notebook, an answer with no question. It took the two greatest ideas of modern physics, born decades after Planck, to reveal why this length matters. And the reason lives in how the number was built. Three of the mightiest forces in the universe had to shake hands to make it, and they almost never touch. Every giant in physics usually keeps to its own kingdom. This chapter is about the one address where three of them are forced to meet. To make the Planck length, Planck reached for three numbers, and each one is the crown jewel of a different empire. The first is the speed of light. This is the law of the very fast. It rules anything racing across the cosmos, from starlight to radio waves, and it sets the ultimate speed limit that nothing can break. Whenever things move near light speed, reality itself bends. Time slows down, distances shrink. This is the world Albert Einstein cracked open, the world of the huge and the swift. The second is the strength of gravity. This is the law of the massive. Gravity is the gentle giant that holds you to the ground, keeps the moon circling the Earth, and binds whole galaxies together across millions of miles of empty space. It is the weakest of all the forces, so weak that a tiny magnet can lift a paperclip against the pull of the entire planet. But gravity has infinite reach, and over cosmic distances it shapes everything. The third number comes from the quantum, the law of the very small. Down among atoms and particles, the world stops being sensible. Things jitter and blur. A particle can be in many places at once. Certainty dissolves into a game of chance. This is the strange kingdom of the tiniest things, where solid rules melt into probabilities. Now look at what makes these three so odd together. The speed of light rules the fast. Gravity rules the heavy. The quantum rules the small. In everyday life, and even in most of physics, they never all matter at the same time. A falling apple obeys gravity, and you can ignore the quantum. A single electron obeys the quantum, and its gravity is so laughably weak you can forget it exists. The kingdoms stay politely separate. Planck's length is the one place where the borders collapse. It is the scale where something is so small that the quantum screams, and at the same time so extreme that gravity, the weakling, suddenly roars as loud as everything else. To even talk about this length, you need light, gravity, and the quantum all speaking at once, in the same breath, about the same speck of reality. That has never happened cleanly in any experiment. We have machines that master the quantum. We have theories that master gravity. We have never built a single working theory that masters both in the same place, because they only both matter here, at this impossibly tiny size, where we cannot reach. So the Planck length is far more than a small number. It is a meeting point, a crossroads where the rules of the giant, the heavy, and the tiny all crash into one another. And when those three rulebooks are forced to share one address, they start to disagree, violently. Their equations stop giving sensible answers and start spitting out nonsense, infinities, and contradictions. That collision is the real reason this length frightens physicists. It marks the doorway to a place where our finest science falls apart. Before we step through that doorway, though, we need the other measurements Planck found hiding alongside his length. Because a length was only the beginning, he also found the shortest possible slice of time. And it is even harder to believe. If space has a smallest step, then ask the obvious follow-up. Does time have a smallest tick? When Planck combined his three magic numbers to build a length, the same trick handed him something else for free: a duration, a stretch of time so brief it makes the blink of an eye look like an entire ice age. We call it the Planck time, and it is the shortest meaningful moment in all of physics. Here is one way to feel it. The Planck time is how long light takes to cross a single Planck length. Light is the fastest thing that exists. In 1 second, a beam of light can circle the Earth more than 7 times. Yet even that blazing speed, crossing the smallest possible distance, takes only the Planck time. So this is the quickest event the universe seems able to hold, the tiniest gap between a before and an after. How brief is it really? Take 1 second, the time it takes to say the word now. Now chop that second into a billion pieces. Take one of those slivers and chop it into a billion pieces again. Do that whole thing 5 times over, and you are finally in the neighborhood of the Planck time. The universe is nearly 14 billion years old, and even so, there have been fewer Planck times since the Big Bang than there are Planck lengths across a single grain of sand. Numbers this extreme stop meaning much on their own, so sit with the strangeness instead. This tiny tick may be the frame rate of reality. Think of a movie. It looks like smooth, flowing motion, but it is really a stack of still pictures flashed one after another, 24 frames every second. Your eye blends them into life. Some physicists suspect the universe might work the same way. Time may not flow like a river at all. It may click forward in the tiniest possible steps, one Planck time after another, so fast and so smooth that we never feel the clicks. Every moment you have ever lived could be built from a mind-melting number of these frames. Nobody knows for certain whether that picture is true. It remains one of the fiercest arguments in physics, and we will return to it later in the journey. But the Planck time does something even bolder. It draws a line across history that no clock can cross. Rewind the universe. Run the Big Bang backwards, squeezing everything closer and hotter and denser, all the way back toward the very first instant. Our best theories can trace that story back astonishingly far. They can describe the universe when it was a tiny fraction of a second old, but they slam into a wall at one specific moment. That moment is the Planck time after the beginning. Before that first tick, our physics goes blank. Our equations stop working entirely. Whatever happened down there, we have no language for it. Asking what came earlier is like asking what is north of the North Pole. The question sounds fine, yet it points nowhere. Time, as we understand it, simply has no before that early. So the shortest tick is also the edge of history, the earliest moment we can ever hope to describe. Space has a smallest step. Time has a smallest tick. And that pattern raises a chilling promise about a third thing Planck measured, a thing that turns out to be nowhere near as small as you would expect. Everything about the Planck scale has been shrinking toward nothing. So brace yourself, because the next measurement breaks the pattern completely. Planck built a smallest length and a shortest time. Naturally, you would expect his measurement of mass to follow the same script, some absurdly tiny weight far below a single atom. The universe had other plans. The Planck mass, the weight that pops out of Planck's magic numbers, is about 21 millionths of a gram. In our everyday world, that is still very light. It is roughly the mass of a single flea's egg, a speck you could rest on your fingertip without feeling a thing. You could hold it, weigh it on a sensitive scale, almost see it. For a human, it is nothing special. But hold on. Everything else at this scale was unthinkably, brain-breakingly small. And here, suddenly, is a weight you can picture, a flea's egg. That is bizarre. And it gets stranger the moment you compare it to the world it supposedly belongs to. The Planck mass is supposed to describe the deepest layer of the tiny. So compare it to the tiny. A single proton, one of the specks inside every atom, weighs almost nothing at all. The Planck mass is about 10 billion times heavier than a proton. Written out, that is a 1 with 19 zeros behind it. On the scale of particles, a flea's egg is not small. It is a monster. It is like learning that the smallest fish in the ocean secretly outweighs a mountain. So why does this spec matter so much? Because the Planck mass marks a border, a line where two completely different worlds meet and blur into one. On one side of the line lives the quantum, the realm of particles. Every particle has a fuzzy, blurry size, a region where it could be found. The lighter the particle, the fuzzier and more spread out it is. The heavier it gets, the tighter and smaller that fuzzy region becomes. On the other side of the line lives gravity and its most extreme creation, the black hole. Any lump of mass, if you crush it small enough, becomes a black hole, a pit in space so deep not even light climbs out. The more mass you have, the bigger the black hole. Now watch these two sizes shrink toward each other. As you pile mass onto a particle, its quantum fuzziness shrinks. At the very same time, the size it would need to become a black hole grows. At one exact weight, the two sizes meet. The blurry quantum region and the black hole boundary land on the very same tiny circle. That weight is the Planck mass. Picture what that means. A single object sitting right at the Planck mass would be a particle and a black hole at the same instant, a thing our physics has no name for. It would be a creature from both kingdoms and neither, standing exactly on the fence between the quantum and gravity. That is why a humble flea's egg marks the frontier of known science. It is the weight where the rules of the small and the rules of the heavy collide inside a single object, and that collision hints at something dangerous. If you ever tried to look at the Planck length directly, this deadly meeting of particle and black hole would rise up to stop you. Which raises a simple question with a horrifying answer. Why can't we just build a better microscope? We can photograph atoms. We can smash particles into pieces. So why not just zoom all the way down to the Planck length and take a look? The answer reveals a trap built into the universe itself. Start with how seeing actually works. To look at anything, you bounce something off it. Your eyes catch light bouncing off this page. To see something small, you need to bounce something small against it. And here, small means a short wavelength. Waves have a length, a distance from one ripple to the next. If your wave is too long and lazy, it rolls right over a tiny object without noticing it, the way an ocean swell ignores a pebble. So to see smaller things, scientists use waves with shorter and shorter ripples. Ordinary light, the kind your eyes use, has ripples far too long to reveal an atom. That is why the best light microscopes hit a wall long before they reach atomic size. To go smaller, you need something with a tighter wave. Here is the catch that changes everything. Shorter waves carry more energy. This is a strict rule of the quantum world. Squeeze a wave's ripples closer together and its energy climbs. A gentle radio wave, with ripples miles apart, carries almost no punch. A tight X-ray wave, with ripples smaller than an atom, carries enough energy to pass through your skin. Push the ripples smaller still, and the energy keeps soaring. Now you can feel the trap closing. To see the Planck length, the smallest step in space, you would need a wave whose ripples are as small as the Planck length itself. And a wave that tightly wound would carry a staggering amount of energy packed into a staggeringly tiny space. This is where the dream dies. To probe the Planck length, you must aim an unimaginable amount of energy at a single, unthinkably small point. And you already learned what happens when you concentrate too much mass or energy into too small a space. It was hiding in the last chapter, in the story of the flea's egg. Cram enough energy into a tiny enough spot, and gravity takes over. The energy behaves like mass, the mass collapses, and a black hole is born. So the closer you try to look, the more energy you must fire at the target. And the more energy you fire, the harder gravity squeezes. Right at the Planck length, the energy you would need to see anything is exactly the energy that folds space into a black hole. Your microscope fails in the strangest way possible. It swallows the very thing you were trying to see. Picture trying to study a snowflake by blasting it with a blowtorch, except 1,000 times worse. The instant your light is sharp enough to reveal the Planck length, that same light collapses into a tiny black hole and hides the view behind a wall of pure darkness. Every attempt to look closer creates the one object that makes looking impossible. No better lens will save us. No cleverer design will sneak past it. The trap is written into the laws of nature themselves. Space seems to guard its smallest secret with a defense no technology can beat, which means the Planck length may be a true flaw, a genuine minimum size below which the word smaller stops making sense. And if that is real, it changes what distance even means. Every wall you have ever met just sits there. The wall at the Planck length does something no wall should be able to do. It fights back. We ended the last chapter with a shocking idea. Try to look below the Planck length and you create a black hole. Let us slow down and stare at that, because it is one of the strangest results in all of science. And it turns a simple size limit into something almost alive. Normally, smaller is a safe word. You can always imagine cutting a distance in half. Half of a mile is half a mile. Half of an inch is half an inch. Half of an atom's width is still a real length. Our whole life trains us to believe distance can shrink forever, smoothly, with nothing ever pushing back. The Planck length shatters that training. As you try to examine smaller and smaller distances, you must pour in more and more energy, just as we saw. That energy warps the space around it. And right at the Planck length, the warping becomes so severe that space caves in on itself and forms a black hole exactly the size of the region you were trying to measure. Here is the part that should raise the hair on your arms. The black hole you create is the same size as the distance you were probing. So if you push even harder, hoping to see something a little smaller, you only make a slightly bigger black hole. The closer you aim, the more the darkness spreads to meet you. The wall does more than block you. It grows toward you, matching your every effort to break through. This flips the whole idea of smallness upside down. Below the Planck length, trying to measure a shorter distance gives you a larger black hole instead. Distance starts running backwards. The very act of asking what is smaller than this produces something bigger. At that point, the question collapses under its own weight. Smaller than the Planck length becomes a phrase with no meaning, like asking for a shape with fewer than 0 sides. That is why many physicists treat the Planck length as a genuine flaw for space itself. It behaves like a true minimum, a smallest possible size baked into reality. Below it, the words here and there may lose all meaning because you can never separate 2 points by less than this distance without space swallowing the gap between them. Let this reshape how you picture the world. You probably imagine space as a smooth, endless backdrop, a stage that can be sliced as finely as you like. This wall suggests the stage has a grain, a smallest possible size, a point past which the smooth picture simply stops. Reality may come in a smallest possible pixel, and the Planck length may be its width. We have left the world of a hard engineering problem. We are talking about the structure of space being fundamentally different from what your eyes and your gut insist. Somewhere far below the atom, the familiar, flowing space of everyday life gives way to something we do not understand and cannot reach. So if we cannot reach it with light, the obvious next thought is to reach it with force. Build a bigger machine, smash particles harder than ever before. Surely, with enough power, we could punch our way down to the Planck length. Physicists ran the numbers on exactly that dream. The size of the machine it would take is almost funny. If light cannot show us the Planck length, then let us try brute force. Let us smash our way in. This chapter is about the machine that job would require, and why it may be the most hopeless building project ever imagined. To reach tiny distances, physicists build particle accelerators. These are enormous rings where particles get whipped up to nearly the speed of light and slammed together. The harder the smash, the deeper into the tiny world we see. The biggest one humans have ever built is the Large Hadron Collider, buried in a ring 17 miles around beneath the border of France and Switzerland. It is one of the most complex machines our species has ever made. The Large Hadron Collider is a triumph, It found the famous Higgs particle. It recreates conditions from a sliver of a second after the Big Bang. It is, by any human standard, mighty. So how close does this magnificent machine get us to the Planck length? Almost nowhere. The gap is so vast it is hard to hold in your head. To reach the Planck length, you would need to smash particles together with an amount of energy called the Planck energy. And our greatest effort, the Large Hadron Collider, falls short of that target by a factor of about 1,000 trillion. Written out, that is a 1 with 15 zeros. Our best machine reaches only a tiny fraction of the way there. So physicists ask the natural question, how big would a collider have to be to close that gap? If our 17-mile ring gets us this far, how large a ring do we need to go all the way? The answer lands somewhere between absurd and heartbreaking. Using the same basic technology as today, a collider powerful enough to reach the Planck energy would have to be staggeringly large. Some careful estimates put its size at bigger than our entire solar system. Others, using different assumptions, stretch the machine out to thousands of light years across. A ring so wide that light itself would take thousands of years just to travel around it once. Sit with that comparison. Our current champion is 17 miles around. The dream machine might need to span the distance between the stars. You could not build it on Earth. You could not build it in our solar system. You would need to reshape a chunk of the galaxy into a single scientific instrument. And even then, you would be pushing against limits nobody knows how to beat. This is why some physicists say, half joking and half crying, that only a civilization far beyond ours could ever directly probe the Planck scale, a society able to bend whole star systems to its will. For us, with our 17-mile ring and our clever tricks, the Planck length sits behind a barrier of pure scale we may never cross. So we are stuck in a strange place. We have a number handed to us by nature that marks the smallest step in space. We have strong reasons to believe it is a true flaw to reality, and we have almost no way to reach it, to test it, to see it with our own machines. It hides behind walls of energy and walls of size, both impossibly high. Yet physicists chase this scale for one deeper reason. What waits on the far side? Because at the Planck scale, the two greatest theories in all of science stop agreeing, and when they clash, they do more than argue. They tear each other apart. Modern physics rests on two towering ideas. At the Planck scale, they meet, and they cannot stand each other. The first great idea is Einstein's picture of gravity, called general relativity. It rules the world of the huge. Stars, galaxies, black holes, the whole shape of the cosmos. In this picture, space and time form a smooth, flexible fabric. Massive objects sink into that fabric like a bowling ball on a trampoline, and the dents they make are what we feel as gravity. This theory is gorgeous, and it has passed every test we have ever thrown at it. It describes the biggest things with breathtaking accuracy. The second great idea is quantum mechanics. It rules the world of the tiny, atoms, particles, the flicker of light. In this picture, nothing is smooth or certain. Everything jitters. Particles blur into clouds of maybe. Energy comes in tiny lumps, and events happen by chance rather than command. This theory is also gorgeous, and it too has passed every test. It describes the smallest things with breathtaking accuracy. Two theories, both perfect in their own kingdom. There is only one problem. They describe reality in ways that flatly contradict each other. General relativity insists that space and time are smooth and continuous, a flawless fabric you can bend and stretch as finely as you please. Quantum mechanics insists that at the smallest scales, everything trembles and churns, nothing sits still, and certainty dissolves. One demands a calm, smooth stage. The other demands a wild, shaking one. For most of the universe, this clash never surfaces, because gravity and the quantum rarely rule the same place at the same time. You already know the one address where they are forced together, The Planck scale. Down there, something is small enough that the quantum roars and extreme enough that gravity roars too. Both theories must speak at once, and the moment they do, the equations detonate. When physicists try to combine the two to describe gravity in a place where the quantum cannot be ignored, the math stops working. The calculations spit out infinity, true infinity, an answer that means the theory has broken. It is the mathematical version of a scream, a signal that we have pushed our finest tools past their breaking point. Every attempt to force gravity and the quantum into the same tiny room ends in this same collapse. Think of two flawless maps of the same city. One shows every street in perfect detail, but claims the ground is glassy and smooth. The other shows every building in perfect detail, but claims the ground is a churning, boiling sea. Each map works beautifully in its own part of town. Lay them over the exact same corner, though, and they describe two different worlds. That corner is the Planck scale, and right now we have no single map that gets it right. This is the deepest unsolved problem in physics. We have two supreme theories, each proven, each trusted, and they simply cannot both be true in the same place. Somewhere at the Planck scale, one of them, or both, must give way to a deeper theory nobody has finished writing. So what actually happens down there, in the place where smooth space and trembling quantum are forced to share one address? One of the greatest physicists of the last century dared to imagine it, and the picture he painted was of a space that boils. Imagine sinking down toward the Planck length and watching smooth, calm space slowly come to a boil. That nightmare picture has a name, and it came from one of the boldest minds in physics. His name was John Wheeler, an American physicist famous for turning impossible ideas into vivid images. He gave the black hole its name, and when he thought hard about what space must look like at the Planck scale, he came up with a word that stuck: foam. Space, at the very bottom, may be foam. Here is how he reached that strange idea. In the quantum world, nothing ever holds perfectly still. Even in the emptiest vacuum, energy flickers and trembles, borrowing and repaying itself in tiny bursts. On the scale of atoms, these flickers are gentle, a soft background hum you can mostly ignore. But the quantum rules say the trembling grows wilder the smaller you look. Now carry that idea all the way down to the Planck length. There, the trembling becomes a storm. The energy flickers grow so violent that, thanks to gravity, they warp the space around them. Space stops being a smooth sheet. It bulges and dips and twists on the tiniest scale. Tiny black holes may pop into being and vanish in less than a Planck time. Bridges and tunnels in space might briefly open and snap shut. The whole idea of a clean, flat backdrop dissolves into churning chaos. That is quantum foam, a picture of space at the smallest scale as a wild, frothing, ever-changing sea. From far away, it looks perfectly smooth, the way it does to us. Zoom in close enough, and the smoothness breaks into a bubbling, seething froth that never rests. Picture the ocean seen from an airplane window. From miles up, the sea looks like a flat, glassy blue sheet, calm and unbroken. You could swear it was perfectly smooth. Now drop down to the surface in a small boat. Suddenly that flat sheet becomes a churning mess of waves and foam and spray, tossing and crashing in every direction. Wheeler's claim is that space plays the same trick. The smooth space we live in is the view from the airplane. Down at the Planck length, we reach the surface of the water, and it is chaos. This idea is beautiful and unsettling for the same reason. It means the calm, dependable space you move through every day is a comforting illusion, a large-scale average of something furiously restless underneath. The stillness is real for us, at our size, but it is stitched together from a storm we are far too big to feel. Nobody has ever seen quantum foam. It lives at the Planck length, behind the walls we already know we cannot cross. It remains a hypothesis, a bold guess about the true nature of space. but it flows naturally out of combining the quantum with gravity, and many physicists take it seriously as a clue about what reality is made of at the bottom. And Wheeler's foam raises a haunting possibility. If space bubbles and froths at the smallest scale, then maybe space itself is built from tiny separate pieces, like a beach that looks smooth from afar but is really countless grains of sand. That single idea splits physics into rival camps, each with a daring answer to the same question. Is space made of pixels? Look at any screen closely enough, and the smooth image shatters into a grid of tiny squares. Some physicists believe reality might hide the same secret. Zoom in far enough, and space itself may break into pixels. This is one of the biggest questions the Planck scale forces on us. In everyday life, space feels perfectly smooth and continuous. You can slide your hand through the air in one unbroken motion. There seem to be no steps, no gaps, no grid. Between any 2 points, you can always imagine a point exactly halfway between them, forever. That smooth, endless picture has guided physics for centuries. But the Planck length whispers a different story. If there truly is a smallest possible distance, a step you cannot cut in half, then space must be grainy at the bottom. It would come in tiny chunks, a smallest unit below which distance stops meaning anything. Space would be built from countless minuscule tiles, each about a Planck length wide. Think of a photograph on your phone. From a normal distance, it looks like a smooth, flowing image, full of soft curves and gentle shades. Now zoom in as far as the phone allows. The curves break apart into little colored squares, the pixels. There is no such thing as half a pixel. The picture has a smallest possible piece. The pixel is where the zooming ends. Some physicists suspect space works exactly like that image, smooth at our scale, yet pixelated once you reach the Planck length. This is a wild claim, and it clashes head-on with the smooth space of Einstein's theory. If space is truly pixelated, then a moving object does not glide continuously. It advances in the tiniest possible hops from one pixel of space to the next, so fast and so small that the motion looks perfectly smooth to us. Reality itself would be a kind of ultra-fine grid, and everything that happens would happen on that grid. There is a thrilling reason to like this idea. A smallest pixel would tame the infinity problem. Remember how the equations exploded into infinity when gravity met the quantum. A lot of that trouble comes from letting space be cut into ever smaller pieces without end, all the way down to zero. But if space has a smallest tile, the cutting stops. There is no zero size to fall into, no bottomless pit for the numbers to plunge down. The infinities have nowhere left to grow, and the math might finally settle down and behave. So a pixelated universe is tempting. It could calm the wild equations and give space a solid floor, but it comes at a price. It means giving up the smooth, flowing space that Einstein's gravity depends on. And physicists do not surrender that picture lightly. This is where the world's smartest people split into rival teams. Everyone agrees something strange happens at the Planck scale. They fiercely disagree about what. One camp has spent decades building a detailed theory in which space really is stitched together from tiny pieces, woven like a fabric from the smallest possible threads. They even claim to know the size of the smallest possible patch of area. Their theory carries a strange and beautiful name, and it pictures space as something closer to chainmail than to glass. What if space is a fabric, woven from unthinkably small threads? An entire branch of physics has spent decades chasing exactly that idea. It is called loop quantum gravity, and it takes the pixel idea and runs with it as far as it will go. In this theory, space itself is built from tiny threads, unimaginably small loops, linked together into a vast web. The loops themselves are the space. Everything you see, every star and stone and breath of air, rests on this hidden weave. Picture a knight's chainmail armor. From across a room, it looks like a smooth, grey, flowing sheet of metal. Step closer, and you see the truth. It is thousands of tiny metal rings, hooked together into a mesh. The smoothness was an illusion created by the sheer number of rings. Loop quantum gravity says space works the same way. What feels like a smooth, empty room is really a mesh of countless loops, so fine that we glide through them without ever noticing the links. Here is the boldest part of the theory. It claims there is a smallest possible piece of area. Just as the pixel idea gives space a smallest length, loop quantum gravity gives space a smallest patch of surface, a tiniest possible tile you could never chop in half. Area itself comes in lumps. You cannot have a region smaller than that smallest tile, in the same way you cannot have less than one brick in a wall. Space is quantized, meaning it comes in whole units, like money that stops at a single penny. This changes the very meaning of empty. In this picture, a patch of empty space is a busy thing, a network of loops carrying a specific structure with a definite smallest size and a definite way of linking up. Emptiness has parts. The vacuum has architecture. What you think of as pure nothingness would be a rich, woven object at the Planck scale, alive with structure too small for any eye or machine to catch. And this weave does something wonderful to the old nightmare of the singularity. At the center of a black hole, Einstein's smooth space predicts a point of infinite density, a place where the math screams and everything falls to zero size. But if space has a smallest possible tile, then nothing can ever be crushed down to a true zero. The weave refuses to be squeezed past its smallest thread. Some versions of this theory suggest that matter falling into a black hole gets crushed almost to nothing, then bounces, because the loops simply will not allow it to collapse any further. That single idea reaches all the way back to the birth of the universe. If space cannot be crushed to zero, then the Big Bang may not have been the true beginning. Run time backwards, and instead of everything collapsing into an impossible point, the weave of space might squeeze down, refuse to break, and bounce. Our universe could be the rebound from an earlier one, a great cosmic breath in a cycle we can barely imagine. Loop quantum gravity is one of the two leading attempts to describe the Planck scale. It is elegant, and it takes the graininess of space seriously, right down to the smallest tile. But it has a fierce rival, a completely different theory that agrees. Space has a bottom while disagreeing about almost everything else. That rival says the tiniest things in existence are tiny vibrating strings, and it may be the most famous idea in modern physics. The most famous attempt to tame the Planck scale rests on one wild claim. The smallest things in the universe are tiny strings, and they are always vibrating. This is string theory, and for decades it has been the boldest idea in physics. For 100 years, we pictured the basic building blocks of matter as points, specks with size 0, infinitely small dots. String theory throws that picture out. It says that if you could zoom down to the deepest level, past the quarks, past everything, you would find that each fundamental particle is actually a minuscule loop or line of vibrating energy, a string. And the length of these strings is right around the Planck length. Here is the idea that makes string theory sing. Every string vibrates, like the string on a guitar. And just as a guitar string can play many different notes depending on how it wobbles, these cosmic strings can vibrate in many different patterns. Each pattern of vibration shows up to us as a different particle. One vibration looks like an electron, a different vibration looks like a quark, another looks like a particle of light. The entire zoo of particles that make up you and everything around you would be a single kind of string, playing different notes. Sit with how beautiful that is. In this view, the universe is a kind of music. Every particle is a note. Every material is a chord. All the endless variety of matter comes from one instrument, vibrating in countless ways at the Planck scale. The old idea of tiny hard specks gives way to a picture of tiny trembling strings, and the difference between iron and air and starlight becomes a difference in how those strings dance. String theory also offers a peace treaty in the war between gravity and the quantum. Remember that the trouble started because point particles have zero size, which let the equations shrink distances down to zero and explode into infinity. Strings fix this by having a size. A string is about a Planck length long, so it can never be squeezed to a true 0 point. That smallest length smears out the violent collisions that used to produce infinity. The math calms down. For the first time, gravity and the quantum can sit at the same table without the equations detonating. But string theory asks for something staggering in return. For the music to work, for the strings to vibrate correctly, the universe cannot get by with just the three directions of space, left and right, up and down, forward and back. The equations only balance if there are extra hidden dimensions of space, curled up so impossibly small that we never notice them. These extra dimensions would be wound up tighter than the Planck length, folded into every point of the space around you, invisible and unreachable. So string theory hands us a breathtaking trade. It promises to unite all of physics, to explain every particle as a note on a cosmic string, and to end the war with gravity. In exchange, it demands hidden dimensions and strings we can never directly see because they live at the Planck scale, behind the same walls we keep running into. Two grand theories now stand before us. One weaves space from loops. One builds everything from vibrating strings. They fight about nearly everything. Yet on one deep point, these bitter rivals quietly agree. And that agreement may be the strongest clue we have that the Planck length is real. Two of the greatest theories in physics can barely stand each other, so when they agree on something, you should lean in and listen. And on one strange point, they nod in perfect unison. We have met the two great rivals racing to describe the Planck scale. One pictures space as a woven mesh of loops, with a smallest possible tile of area. The other pictures reality as tiny, vibrating strings, each about a Planck length long. They disagree about what space is, what particles are, how many dimensions exist, and almost every other detail. Their supporters have argued for decades, sometimes bitterly. Yet underneath the feud lies a buried agreement, and it is a powerful one. Both theories say there is a smallest meaningful length in the universe. Both say you cannot keep shrinking distances forever. Both draw a line at the bottom of space, and both draw it at the Planck length. Loop quantum gravity reaches this floor through its smallest tile of area. In that theory, you cannot chop space into pieces below a certain size, because area itself comes in whole lumps. String theory reaches the same floor through the size of its strings. Since the smallest object is a string about a Planck length long, nothing smaller can ever be built or probed. Two completely different roads, starting from completely different ideas, arrive at the very same doorstep. That is the kind of clue physicists treasure. When two theories built on opposite foundations stumble onto the same answer, it hints that the answer is telling us something true about reality, rather than something one theory simply assumed. It is like two explorers setting out from different continents, sailing by different stars, using different maps, and washing up on the exact same tiny island. The island starts to feel real, and the island they both find is this. The Planck length is a genuine flaw, a smallest step, a true minimum size baked into the fabric of the world. Below it, the idea of distance may dissolve completely, the way we saw when a shorter distance turned into a bigger black hole. The universe seems to have a bottom, and our two best guesses about that bottom point to the same place. This shared flaw reshapes the oldest question in this whole story, the one we started with. Can you cut something in half forever? For thousands of years, the honest answer was a shrug. Now, from two directions at once, physics leans toward a firm reply. No, the cutting stops. Somewhere around the Planck length, the very meaning of half as small runs out, and reality refuses to be divided any further. Their agreement does not mean we have solved the Planck scale. Both theories are unfinished, unproven, and impossible to test directly with any machine we can build. The war between them still rages, and either one could turn out wrong. But their quiet agreement on a smallest length stands as one of the most striking hints in modern science. When your fiercest rivals agree on where the ground is probably there. So, space may have a flaw, time may have a shortest tick, And now a new question rises, hotter than any we have asked. If length and time both bottom out at the Planck scale, what happens to heat? Is there a hottest possible temperature? The answer takes us to a number so extreme, it makes everything so far look tame. There is a coldest possible temperature, the deep freeze where all motion stops. Now, turn the dial the other way and ask the opposite question. Is there a hottest possible temperature? The Planck scale says yes, and the number will stagger you. Temperature is really about motion. When something heats up, its particles jiggle and race faster. Cold is slow, hot is fast. Warm your hands by a fire, and you are speeding up the tiny particles in your skin. At the low end, there is a hard floor. Cool anything down enough and its particles stop moving, a point called absolute zero. You can never go colder because there is nothing slower than fully stopped. For a long time, the top end looked wide open. Heat something up, and its particles just move faster and faster, with seemingly no ceiling, faster and faster forever. But the Planck scale closes that door too. Push the temperature high enough, and you reach a limit called the Planck temperature. It is the hottest anything can meaningfully be. Brace yourself for the number, because words struggle to hold it. The Planck temperature is about 100 million degrees. That is a 1 followed by 32 zeros. Compare that to the center of our sun, a furnace so hot it powers all life on Earth from 93 million miles away. The sun's core sits at around 27 million degrees. The Planck temperature is so much hotter that the blazing heart of the sun, next to it, is basically ice cold. You could line up trillions of suns and still not come close. Why is there a ceiling at all? The reason ties back to everything we have learned. As you heat something, its particles carry more and more energy. Push toward the Planck temperature, and the particles carry so much energy, crammed into such small spaces, that you hit the same deadly trap from before. The energy becomes so concentrated that gravity takes over and space itself starts to buckle. Right at the Planck temperature, the heat is so extreme that tiny black holes would begin to form straight out of the raw energy. So the hottest possible temperature is the point where heat becomes so violent that it warps space into black holes. Try to go hotter, and you no longer get a hotter substance. You get collapsing space and a froth of tiny black holes, the same wall we keep meeting, now dressed as heat instead of distance. Every road at the Planck scale seems to end in the same place, where energy and gravity fold reality shut. There is something almost poetic about it. The coldest limit is a world frozen into perfect stillness. The hottest limit is a world so furious it tears the fabric of space. Between those two edges lies every temperature that has ever existed, every fire, every star, every frozen moon. All of it fits inside the range the Planck scale allows. And this ceiling is far more than a curiosity. There was a time when the entire universe actually sat at nearly this unimaginable temperature. Not a small patch, everything, everywhere, all at once, hotter than the core of any star that would ever form. It happened at the only moment extreme enough to reach the Planck temperature, the very first instant of the universe. A single Planck time after the Big Bang, when the cosmos was young, tiny, and hotter than hot has any right to be. Rewind the entire history of the universe, all the way back to its very first instant, and you arrive at a moment so extreme that all of physics stands on the edge of a cliff. Welcome to the Planck epoch, the opening tick of everything. We have spent this whole journey shrinking down in space to reach the Planck scale. Now we travel through time instead, backwards, toward the beginning. The universe has been expanding and cooling for nearly 14 billion years. Play that film in reverse, and everything rushes together, growing hotter and denser and smaller with every step back. Keep rewinding, past the first galaxies, past the first atoms, all the way to the earliest sliver of time we can name. That sliver is the Planck epoch, It stretches from the very beginning to just one Planck time afterward, the shortest tick we met earlier. During this unimaginably brief first moment, the entire universe was squeezed into a space smaller than anything we have words for, and it blazed at nearly the Planck temperature, the hottest heat that can exist. Everything that would ever become galaxies, stars, planets, and people was packed into that furious, tiny, roaring point. And here is what makes the Planck epoch so special and so maddening. It is the one time in all of history when the entire universe was small enough and hot enough to live at the Planck scale. The whole cosmos was Planck-sized. That means the quantum roared and gravity roared everywhere, for every speck of everything, all at once. The clash we have chased this entire journey, the war between the quantum and gravity, filled all of reality back then. It was everywhere, in every corner, at the very same instant. Which leads to a humbling truth. Our physics cannot describe the Planck epoch. Remember that gravity and the quantum, forced together, make our equations explode into infinity. During the Planck epoch, they were forced together across the whole universe. So our finest theories go completely blank at the dawn of time. We can describe the universe a heartbeat later, once it cooled and spread just enough for the quantum and gravity to separate. But that very first tick stays locked away, guarded by the same wall we keep colliding with. Weigh what that really means. The birth of everything, the single most important event in the history of reality, happens inside a moment our science cannot yet read. All our telescopes, all our theories, and the opening instant of the cosmos remains a sealed room. We can stand at the door. We can describe the hallway just outside. The room itself stays dark. The forces we know today were all tangled into one back then. Gravity and the forces that rule particles may have been a single unified force during that first tick, only splitting apart as the universe cooled a moment later. To understand the Planck epoch, we would need the very theory nobody has finished writing, the one that finally unites the quantum and gravity into a single map. The beginning of the universe and the smallest scale in physics turn out to be the same locked door, seen from two directions. So the Planck scale is the floor of space, the shortest tick of time, and the veil over the birth of the cosmos itself. And once you realize the beginning is hidden behind this scale, a stranger thought creeps in. Perhaps the deepest secrets of the universe are written in its smallest possible piece, in the tiny grain we can never touch. Our telescopes are time machines. Look far enough into space, and you look into the past. Yet even the greatest telescope ever built slams into a curtain it can never pull back. Behind that curtain hides the beginning. Here is why looking far means looking back. Light travels fast, but never instantly. When you see the sun, you see it as it was 8 minutes ago, because the light took 8 minutes to reach you. When you see a distant galaxy, you see it as it was millions or billions of years ago. So the deeper into space a telescope stares, the younger the universe it catches. Point a powerful telescope far enough, and you are watching the cosmos in its childhood. Astronomers have ridden this trick almost all the way back. They have captured the oldest light in existence, a faint glow that fills the entire sky in every direction. We call it the cosmic microwave background, and it is a baby photo of the universe, taken when the cosmos was only about 380,000 years old. Every telescope that studies it is peering as far back in time as light itself allows. But that baby photo is also a wall. Rewind past it, and something strange happens. The early universe was a thick, blazing fog, so hot and so crowded with particles that light could not travel in a straight line. Light bounced and scattered endlessly, trapped the way a car's headlights drown in dense fog. For the first few 100,000 years, the whole universe was opaque. No light escaped to carry us a picture. The cosmic microwave background is the moment the fog finally cleared, when the universe cooled enough to turn transparent and let light fly free at last. That first freed light is the oldest thing any telescope can ever see. Everything before it is hidden behind the fog, sealed off from every camera and every eye. Now remember how far back the Planck epoch sits. The oldest light comes from a universe hundreds of thousands of years old. The Planck epoch happened in the first tiny fraction of the very first second. It lies unthinkably deeper, far behind the fog, far behind the oldest light, in a region no beam of light can ever reach us from. So the birth of the cosmos is doubly hidden. Our theories go blank there, as we saw. And even if they worked, no light could carry the image out. The most important event in all of history sits behind a wall of blazing fog that no telescope will ever pierce. Yet physicists refuse to give up. There may be another messenger. When the universe was born, it likely shook space itself, sending out ripples called gravitational waves. These ripples pass straight through the fog, unbothered, carrying news from before the oldest light. If we ever learn to catch the faintest of them, the ones made in the first instance, we might finally hear an echo from behind the curtain, even while we can never see through it. Until then, the beginning stays sealed, and that silence pushes physicists toward a wild idea. If we cannot look at the Planck scale from the outside, maybe its fingerprints are hiding inside things we already know, even inside a simple question about how anything moves at all. Fire an arrow at a target. It has to fly, obviously. But an ancient thinker found a way to argue, with cold logic, that the arrow can never arrive. His puzzle is 2,500 years old, and the Planck length may finally answer it. The thinker was Zeno, a Greek philosopher with a gift for driving people crazy. Here is one version of his trouble. Before the arrow reaches the target, it must first cross half the distance. Fair enough. But before it can cross that half, it must cross half of the half. And before that, half again. And so on, without end. Follow the logic, and it never stops. To reach the target, the arrow must complete an endless list of steps, each one half the size of the last. Cross half, then a quarter, then an eighth, then a 16th, shrinking forever. There is always another, smaller half to cross first. So, Zeno argued that the arrow can never finish an infinite list of moves. Motion itself becomes impossible. The arrow should hang frozen in the air for all time. Of course, the arrow lands. You can watch it hit. That is what made the puzzle so maddening for thousands of years. Simple logic proved motion was impossible, and yet the world kept moving, mocking the logic. Something in the argument had to be broken, but pinning down exactly what proved slippery. Mathematicians eventually found clever ways to add up an endless list of shrinking numbers and get a sensible, finite answer. That tames the paradox on paper, but it leans on one quiet assumption, the same one we have been circling this whole journey. It assumes space can truly be split in half forever, with no smallest step. Now bring in the Planck length. If space has a genuine flaw, a smallest possible distance, then Zeno's endless halving is a fantasy. You cannot keep cutting the arrow's path in half without limit, because eventually you reach the smallest tile of space, the step that can never be split. The infinite list of moves is finite after all. It has a last, tiniest step that changes everything. In a world with a smallest length, the arrow does not face an endless staircase of ever smaller halves. It faces a huge but countable number of Planck-sized steps. It crosses them one by one and lands. The paradox dissolves, because the trick at its heart, the endless splitting, was never allowed by nature in the first place. This is a beautiful thought. A riddle that stumped philosophers for 2,000 years might have a physical answer buried at the smallest scale of reality. Motion works because space is grainy. The arrow lands because it runs out of halves to cross. Nobody can prove this is the true solution. The Planck length stays beyond our reach, and mathematicians will point out that their infinite sums already settled the matter on paper. But it hints at something profound. The deepest puzzles about motion, space, and infinity may all trace back to one question. Is space smooth, or does it come in smallest pieces? And if space really is built from countable pieces, then a shocking new possibility opens up. Maybe you can count them. Maybe there is a hard limit to how much can fit inside any patch of space at all. That single idea leads to the strangest discovery in this entire story. Picture a box. How much stuff can you cram inside it? How much information? How much memory? How many details can a region of space possibly hold? The answer sounds obvious, and it is completely wrong. Your gut says a bigger box holds more. Double the space inside, and you double what fits. Capacity should grow with volume, with the room inside the box. That is how everything in your life works. A bigger closet holds more clothes. A bigger drive holds more files. Reality disagrees, and the truth is one of the strangest results physics has ever found. The maximum amount of information you can pack into any region of space is set by the area of its surface, the skin around it, rather than the room inside. What limits a box is its wrapping, the surface stretched around it. And here is where the Planck length storms back in. That surface gets measured in Planck-sized tiles. Imagine covering the boundary of your region with the tiniest possible squares, each one about a Planck length on a side. Count those tiles, and you have counted the absolute maximum number of bits of information the region can hold. Every patch of space comes with a pixel budget, and the budget is written on its skin. Grow the surface, and the budget grows with it. Shrink it, and the budget shrinks. A cathedral and a shoebox obey the very same law, each one capped by the size of the wrapping stretched around it, counted in the smallest tiles that exist. Sit with how bizarre that is. To find the most stuff a room could ever contain, you do not measure the room. You measure the wallpaper in the smallest tiles that exist. A region's deepest secret, its total capacity for information, hides on its two-dimensional boundary, tallied one Planck square at a time. This flips our whole picture of space inside out. We live feeling like creatures of volume, moving through a roomy, three-dimensional world. But this rule whispers that the real accounting happens on surfaces, on the flat edges wrapped around things. The inside, the volume we trust so completely, may be the illusion. Where did such a wild idea come from? It came from staring hard at the most extreme objects in the universe, the ones that crush the rules of space and time down to their breaking point, black holes. When physicists tried to answer a simple question about black holes, how much information can a black hole swallow and hide, the numbers led them somewhere no one expected. The answer was tied entirely to the area of the black hole's surface, the boundary of no return around it, rather than to the space locked inside. And that surface, once again, gets measured in Planck-sized tiles. That single discovery cracked open the idea that all of space might keep its books on surfaces rather than in volumes. It suggested a rule reaching far beyond black holes, out to every region of the cosmos, including the room you are in right now. So, a black hole holds the key. To understand why the universe has a pixel budget, we have to look straight into the darkest, densest object nature can make, and ask what happens to information when it falls in. The answer turned a generation of physicists pale. Throw a book into a black hole, and it vanishes. The pages, the words, the ink, all gone past the point of no return. So where does the information go? Chasing that question led to the most jaw-dropping fact in this whole story. First, meet the surface of a black hole. It is called the event horizon, an invisible boundary in space. Cross it, and you can never come back, because escaping would mean traveling faster than light, which nothing can do. Inside the horizon, everything falls helplessly toward the center. The horizon is the edge of a one-way door. Now the puzzle. Physics has a deep rule that information is never truly destroyed. Burn a book, and in principle, the smoke and ash still carry the scrambled record of every word. But a black hole seems to shatter that rule. Toss something in, and it disappears completely behind the horizon. Its information looks erased from the universe. For years, this quietly terrified physicists, because a broken rule this deep threatens all of physics. The resolution came from measuring how much a black hole can remember, and the answer stunned everyone. A black hole's total information, its full hidden memory, is written across its horizon, the surface, tallied in Planck-sized tiles. Here is the exact recipe, and it is gorgeous. Take the surface of the black hole, cover it in the smallest squares that exist, each about a Planck length wide. Count them. For every 4 of those Planck squares, the black hole can store a single bit of information, one tiny yes or no fact. The entire memory of everything that ever fell in gets encoded on the skin, 4 Planck tiles per bit. Let that reshape your picture of a black hole. You imagine it as a bottomless pit, a deep well where things pile up inside. But its capacity to store information depends only on the area of its surface, never on the volume within. A black hole twice as wide across does not hold twice the information. It holds 4 times as much. Because its surface grew 4 times larger, its memory grows with the skin around it. This is where the pixel budget of the universe was born. A black hole is the densest object nature allows. You cannot cram more information into a region than a black hole of that size holds, because trying to pack in more would just collapse the region into a black hole anyway. So the black hole sets the absolute limit, and that limit lives on the surface, counted in Planck squares. The strangeness runs deeper still. It means the full story of a 3-dimensional object, everything that fell into the black hole, all its depth and detail, gets completely captured on a flat, 2-dimensional surface. Nothing is lost. The surface holds it all. A flat boundary, tiled in Planck squares, can carry the entire record of a whole volume of stuff. Read that again, because it is the crack that splits the world open. If a flat surface can hold every detail of the volume behind it, then maybe volume is not as real as we think. Maybe the 3-dimensional world is a kind of projection from a 2-dimensional edge. Maybe everything you see and touch, the whole roomy universe, is being painted from a distant, flat surface you can never visit. That thought has a name, and it may be the most mind-bending idea in modern physics. What if everything around you, the room, your body, the entire sky, is a projection? A 3-dimensional image painted from information stored on a flat surface far away. This is the holographic principle, and serious physicists take it seriously. Start with a hologram you may have seen, the shimmering 3-dimensional image on a credit card or a sticker. It looks like it has depth. Tilt it, and you seem to see around the object, as if it were really sitting there in space. But all of that depth is a trick. The whole 3-dimensional image is stored as a flat pattern etched on a 2-dimensional surface. The depth is an illusion conjured from a flat sheet. Physicists took the lesson from black holes, that a surface can hold every detail of the volume behind it, and asked a daring question. What if the entire universe works this way? What if all the richness of our 3-dimensional world, every star, every planet, every living thing, is really encoded on a vast, distant, 2-dimensional boundary, and the depth we move through is a grand projection from that flat edge? This is the holographic principle. It says the true, fundamental description of a chunk of the universe might live on its surface, written in Planck-sized tiles, while the roomy, 3-dimensional inside is a kind of image conjured from that surface. The volume you trust, the space you walk through, could be the hologram. The flat boundary could be the reality. It sounds like pure fantasy, but this idea earns its keep because it has become one of the most powerful tools in all of theoretical physics. Researchers discovered specific model universes where the math works out perfectly. In these models, a complicated 3-dimensional world full of gravity turns out to be exactly equal to a simpler flat world on its boundary, with no gravity at all. The two descriptions, one with depth and one flat, hold the very same information. They are 2 ways of reading the same book. That discovery electrified physics. It handed researchers a magic trick. When a problem about gravity and black holes becomes too hard to solve in 3 dimensions, they can translate it onto the flat boundary, solve the easier flat version, and translate the answer back. The hologram works as far more than a poetic image. It is a working dictionary between 2 versions of reality, and it lands us somewhere staggering. If the deepest layer of reality is a flat surface tiled in Planck squares, then space itself, the 3 dimensions you have trusted your whole life, may be woven out of something more basic. Depth would be a story the universe tells, spun from flat information at the smallest scale. The Planck length would be the size of the individual threads in that flat weave. Nobody has proven that our own universe is a hologram. The clean examples, where the math works, are model universes, simpler than the real one. Extending it to the cosmos we actually live in remains an open and fierce challenge. But the fact that it works at all, that a flat surface can perfectly stand in for a world with depth, is one of the strongest hints we have about what reality is doing at the Planck scale. So space may be smooth or grainy, solid or projected, which drags the oldest question of all back into the light. If space comes in smallest pieces, does time do the same? Does the clock of the universe tick or flow? Earlier in this journey, we planted a question and promised to return. Now we are back. Does time flow like a smooth river, or does it click forward in tiny, separate ticks, like the frames of a film? At the Planck scale, this becomes one of the fiercest fights in physics. We have seen strong hints that space comes in smallest pieces, a floor below which distance loses meaning. It feels natural to expect time to match. If there is a shortest length, surely there is a shortest tick, the Planck time we met long ago. Many physicists suspect exactly that. In their picture, time advances in the tiniest possible jumps, 1 Planck time at a step. The universe would update itself like a cosmic clock, ticking so fast that the flow we feel is an illusion, stitched together from countless separate instants. There is a real appeal to a ticking universe. If both space and time come in smallest units, then reality starts to look like a vast computation, updating on a fixed grid of space and time. The infinities that plague our equations would have nowhere left to hide, because there would be no infinitely small gaps left to fall into. A grainy time would tidy up a great deal of the mess. But this idea smashes head-on into Einstein, and the collision is brutal. Einstein showed that time runs differently for everyone. How fast your clock ticks, and even which events count as happening at the same moment, depends on how you are moving. 2 people racing past each other disagree about timing, and both are correct. Time stretches and squeezes depending on your speed. Now here is the trap. If time comes in fixed ticks of one exact size, then whose ticks are we talking about? Someone flying past at enormous speed would see those ticks stretched to a different length. The supposedly smallest, universal tick would look bigger or smaller depending on who measures it. A minimum tick that changes size for different observers is a contradiction, and it strikes at the very heart of a chunked time. So physicists are caught between 2 beautiful ideas that refuse to share a room. On one side, the hint that time is grainy, ticking in Planck-sized steps, which would tame the infinities and match a grainy space. On the other side, Einstein's rock-solid discovery that time bends and flows differently for everyone, which a fixed universal tick seems to forbid. Nobody has settled it. Some of the boldest new theories try to have it both ways, building a kind of grainy time that somehow still looks the same to every observer, no matter how fast they move. Others suspect that space and time are not fundamental at all, that they emerge from something deeper, where the whole question of ticking or flowing simply dissolves. We will chase that stranger possibility soon. For now, the honest answer is that we do not know whether the universe ticks or flows. The clock at the bottom of reality stays hidden, its face turned away from us. But there is a way to hunt for graininess without ever reaching the Planck scale directly. It uses the whole universe as a laboratory, and a cosmic explosion billions of light years away as a starting gun. You cannot build a machine to reach the Planck scale. We have hammered that home, so physicists pulled off something clever. If they cannot make the effect bigger, they let it add up over the biggest distances in the universe. Here is the trick. Suppose space really is grainy, a churning foam at the Planck scale, as some theories claim. Then a beam of light crossing it would feel that graininess, like a car feeling a rough road. The idea is that light of different colors, carrying different energies, might travel at very slightly different speeds through grainy space. High-energy light might drag a hair behind low-energy light, snagged a touch more by the tiny bumps. The catch is that the effect would be absurdly small. Over a few miles, or even across our whole solar system, the lag between fast and slow light would be far too tiny to ever notice. The graininess of space, if it exists, is so fine that light glides over it almost perfectly. Almost. And that word is the whole game, because a tiny effect, repeated over a long enough distance, grows into something you can measure. Think of a race between two runners who differ in speed by the width of a single hair per mile. Over 1 mile, you would never spot the gap, but run them across 1,000 miles, then 1,000,000, and that hair-thin difference piles into a lead you can actually see. Stretch the race long enough, and even the tiniest difference becomes obvious. So physicists needed the longest racetrack imaginable, and a flash of light bright enough to survive the whole trip. The universe provides exactly that. Deep in space, dying stars and colliding dead stars unleash the most violent explosion since the Big Bang, called gamma-ray bursts. In a few seconds, one of these bursts can release more energy than our sun will pour out across its entire lifetime. And crucially, a single burst blasts out light across a huge range of energies, all at nearly the same instant. That is the perfect starting gun. All the light leaves together, high energy and low energy side by side. Then it races across the universe toward us, traveling for billions of years, crossing distances so vast that any tiny difference in speed has an eternity to add up. By the time the light reaches our telescopes, even a Planck-scale graininess should have smeared the arrival times apart, with the high-energy light landing a measurable moment behind the low-energy light. All physicists have to do is catch one of these bursts and time the arrival of its different colors with fantastic precision. If the high-energy light shows up late, lagging behind the low-energy light by just the right amount, it would be a fingerprint of grainy space, the first real evidence of the Planck scale bleeding through into something we can measure. It would be a peek behind the curtain, bought with patience and the sheer size of the cosmos instead of a giant machine. In 2009, a telescope built for exactly this hunt caught one of the sharpest, most distant bursts ever seen. 2 photons from that blast, born together, had raced across more than 7 billion years of space to reach it. When physicists compared their arrival times, the result sent a jolt through the field. 2 flashes of light left the same explosion at the same instant. One carried 1,000,000 times more energy than the other. Then they raced across 7 billion years of space toward a waiting telescope. What happened when they arrived rewrote the rules of the hunt. The telescope was NASA's Fermi Gamma Ray Space Telescope, orbiting Earth, built to catch the highest energy light in the universe. In 2009, it locked onto a short, fierce gamma-ray burst, a blast from the distant cosmos so far away that its light had traveled more than 7 billion years to reach us. That is more than half the age of the universe. The starting gun could not have been better. Among the flood of light from that burst, Fermi caught 2 photons that mattered enormously. One was low in energy, the other was staggeringly high, carrying about 1,000,000 times more energy than its partner. If grainy space slows high-energy light even a hair, then across 7 billion years of travel, these 2 photons should have arrived far apart, the high-energy one dragging clearly behind. They arrived together, After a journey of more than 7 billion years, the two photons reached the telescope within a fraction of a single second of each other. The enormous gap in their energy made almost no difference in their arrival time. The high-energy light arrived clean, untouched by any roughness in space. Picture what that means. If space is grainy, its grain is so unbelievably fine that even light stretched across half the history of the universe felt no bumps at all. The measurement was so precise that it tested smoothness right down to the Planck length and even a touch below it. Space, as far as this experiment could see, is smooth all the way to the smallest scale we can name. This result landed hard. It ruled out an entire family of quantum gravity theories. The ones that had predicted high-energy light should slow down in a simple, steady way as it crossed grainy space. Those models made a clear bet that the roughness of space would show up in exactly this kind of race. The photon from that burst collected the bet and proved them wrong. Nature had spoken, and it said the road was smoother than they thought. But hold on, because this is a twist, and its meaning is subtle. The smoothness leaves the Planck scale standing. What it proves is narrower, that any graininess is even finer and gentler than some theories guessed. Space might still be a quantum foam, still built from Planck-sized pieces, just in a way that leaves light alone in the simple manner those particular models predicted would fail. The wall stands. We only learned that it hides its texture even better than we hoped. That is the strange beauty of this search. A single photon, born in a distant catastrophe, crossing 7 billion years of darkness, carried a real message about the smallest scale in existence. We cannot build a machine to touch the Planck length, but the universe, it turns out, has been running the experiment for us all along, and we finally learned to read the results. Still, the smoothness raises a fresh riddle. If space stays perfectly smooth, even for a supercharged photon, then how can it also have a smallest possible length? To answer that, Einstein's own theory has to bend in a way he never imagined. Here is a paradox that should not exist, yet it sits right at the center of everything. Einstein proved that lengths shrink for fast-moving observers. So, if the Planck length is the smallest length there is, whose Planck length are we talking about? Start with one of Einstein's strangest results. When something moves very fast, close to the speed of light, its length shrinks along the direction it travels. This is real, measured, and true. A fast-moving ruler is genuinely shorter than the same ruler at rest, from your point of view. The faster it goes, the more it squeezes. Speeds near light can crush a long object down toward a sliver. Now aim that fact at the Planck length. Suppose the Planck length truly is the smallest possible distance, a hard flaw built into reality. Fine, but now imagine that smallest length rushing past you at nearly light speed. Einstein's rule says it should shrink even further, squeeze down below the Planck length. And that spells disaster, because we just spent this whole journey learning that nothing can be smaller than the Planck length. So which is it? Either the Planck length is truly the smallest, and Einstein's shrinking must somehow stop at that flaw, or Einstein's shrinking has no flaw, and the Planck length looks different to different observers, which means it cannot be a universal smallest step. Two of our deepest ideas, a smallest length and length contraction, refuse to both be fully true in their simple forms. One of them has to bend. Physicists came up with a bold fix, and it copies a trick Einstein himself pulled a century ago. Think about the speed of light. It is bizarre in a very specific way. No matter how fast you chase a beam of light, no matter how you move, you always measure light traveling at exactly the same speed. The speed of light is the same for everyone, a fixed constant that never changes with your motion. That single strange rule is the foundation of Einstein's relativity. The new idea asks, what if the Planck length is like that too? What if it is a second unchanging constant, a length that stays exactly the same for every observer, no matter how fast they move? Just as everyone agrees on the speed of light, everyone would agree on the Planck length. It would refuse to shrink, no matter how close to light speed it flew past you. It would be a universal, unbreakable, smallest step, woven into the rules of motion themselves. This idea has a name, doubly special relativity, because it takes Einstein's relativity and gives it two universal constants instead of one. The speed of light stays the ultimate speed, and the Planck length joins it as the ultimate smallness, a flaw that every observer shares. It is a beautiful patch. It saves the smallest length and keeps everyone agreeing on it. But like every fix at the Planck scale, it charges a price, and the price is strange enough to make your head spin. To keep the Planck length the same for everyone, the rules of space and time have to twist in new ways at the highest energies, in ways that even a supercharged photon might one day reveal. And that twist reaches into the smoothest, most trusted part of Einstein's world, threatening to warp the very fabric he described. Forcing the Planck length to stay the same for everyone sounds tidy, but it tears at the smooth fabric of Einstein's universe, and it creates a puzzle so odd that physicists nicknamed it after a soccer ball. First, the fabric. Einstein's space-time is perfectly smooth and stretchy. You can speed up without limit toward the speed of light, and space keeps squeezing. Distances keep shrinking, with no bottom. That endless, flawless stretching is baked into his equations. To install a rigid Planck length, a smaller step that never shrinks, you have to reach into those equations and stiffen them at the extremes. The smooth, endlessly flexible space-time becomes something that resists, that pushes back, once you get close enough to the Planck scale. One consequence lands right where we were just looking. If the rules of motion change at the highest energies, then the speed of light might depend, ever so slightly, on a light beam's energy. That is the exact thing physicists hunted with distant gamma-ray bursts. So this daring rewrite of Einstein makes a real, testable prediction, and the sky becomes the courtroom. So far, the light from those bursts has stayed stubbornly smooth, which tightly limits how strong the effect can be and rules out the boldest versions. Now the soccer ball. Here is where a rigid Planck energy turns truly weird. The Planck mass, the flea's egg, is also a Planck energy, and in this picture, it becomes a kind of ceiling, a maximum for a single particle, fine for one particle, but a soccer ball is made of a staggering number of particles, and its total energy sails far past the Planck energy with no trouble at all. A thrown soccer ball flies like an ordinary ball, no black hole in sight. So, the new rules face an awkward question. If no single thing can carry more than the Planck energy, why does a soccer ball, made of countless particles, cruise past that limit so easily? Where is the line between one particle, which obeys the ceiling, and a ball of trillions upon trillions of them, which ignores it? Getting the math to treat a lone photon and a whole soccer ball correctly at the very same time turns out to be fiendishly hard. Physicists call it the soccer ball problem, and it remains an open sore in these theories. This is the pattern of the entire Planck scale. Every time we patch one crack, another splits open. Fix the shrinking length, and the fabric of spacetime stiffens in strange ways. Stiffen the fabric, and light speed starts depending on color. Cap the energy of a particle, and suddenly you cannot explain a thrown ball. The clues all point to the same truth, that our current rules are approximations, beautiful and accurate in our everyday world, yet quietly incomplete at the very bottom. None of these ideas is proven. Doubly special relativity might be the key, or it might be a wrong turn that teaches us something on the way past. But it shows how radical the fix might need to be. To make room for a smallest length, we may have to rebuild the rules of space, time, and motion from the ground up. And while some physicists rewrite the rules with pen and paper, others try something sneakier. They build tiny stand-in universes on a lab bench, hoping to watch Planck-scale physics play out in a place they can actually reach. Empty space is a lie. Down at the Planck scale, it may be crawling with tiny black holes that pop into existence and vanish again, faster than you could ever catch them. And those flickering monsters might have their eye on the particles that make up you. Recall the quantum foam, the picture of space boiling at the smallest scale. In that froth, energy flickers wildly, borrowing and repaying itself in tiny bursts. Sometimes, the theory says, a flicker gets violent enough to do something extreme. For the briefest sliver of a Planck moment, a knot of energy warps space so hard that it forms a minuscule black hole, then evaporates almost instantly. These are called virtual black holes, ghostly things that blink into being and blink back out before the universe seems to notice. You could never fall into one of these. They live and die in less than a Planck time, smaller than anything we could detect, part of the restless churn of the vacuum itself. But even a black hole that lasts for the tiniest flicker is still a black hole. And a black hole does one thing above all else. It destroys. Anything that falls in gets scrambled, its identity erased. That is the one unbreakable rule of every black hole, tiny or vast. Now put the two ideas together, and a chilling possibility appears. If the vacuum is full of tiny black holes winking in and out everywhere, all the time, then now and then one of them might blink into existence right on top of a passing particle. For a flicker, that particle would be caught in the grip of a real black hole, and when the little black hole evaporated, the particle might come out changed, scrambled, or gone. This matters most for the most stable bricks of matter, the protons sitting inside every atom. A proton is normally rock solid. It holds its identity for staggering lengths of time. But if virtual black holes really flicker through the vacuum, then every proton in the universe is playing a slow, endless game of chance. Every so often, one of these Planck-scale black holes might blink into being right around a proton, seize it, and tear it apart from the inside. If that happens, even extremely rarely, then protons carry a hidden expiration date. They would decay, fall apart, given enough time, undone by the seething quantum foam of space itself, reaching in with tiny black hole fingers and unmaking them. The most stable object in ordinary matter would slowly dissolve, its doom written by the structure of space at the Planck scale. This is one of the ways the Planck scale, impossibly far below anything we can see, might leave a fingerprint we can actually hunt for. We cannot watch a virtual black hole, but we might be able to watch a proton fall apart, if it ever does. And the rate at which protons decay, or stubbornly refuse to, could tell us whether space really froths with these flickering monsters. So physicists built enormous detectors and went hunting for the death of a proton. What they found, or rather what they have failed to find, turns out to be just as revealing, because so far, across decades of watching, not one single proton has been caught dying. Deep under a mountain in Japan sits a gigantic tank filled with 50,000 tons of ultra-pure water, wrapped in thousands of golden light sensors. Its job is to watch, patiently, for a single proton to die. For decades, it has seen nothing, and that nothing is one of the most powerful measurements in physics. We just met the fear that the Planck scale might make protons unstable, that flickering black holes or other deep effects could slowly unmake them. Several major theories agree that protons should decay, extremely rarely, if our ideas about uniting the forces of nature are right. So physicists set a trap. If a proton dies, it leaves a tiny flash of light as it falls apart. Gather enough protons in one place, watch them closely, and you might catch that flash. Here is the clever part. You do not wait around staring at one proton, hoping it decays. A single proton might last almost forever. Instead, you gather an enormous number of them and watch them all at once. Water is perfect because it is packed with protons, and it is clear enough to see a flash anywhere inside. 50,000 tons of water holds a mind-bending number of protons. If each one has even a tiny chance of dying each year, then among all those countless protons, a few should sputter out every year, and the sensors would catch the flash. So they built the tank deep underground to shield it from the constant rain of cosmic rays, and they waited. Years passed. The golden sensors stared into the water, alert for the telltale flash of a dying proton. And across all those years, watching all those protons, they have caught none. The protons simply refuse to die. That silence is data of the highest order. From it, physicists worked out just how stable the proton must be. The number is staggering. A proton lives, on average, at least about 1 trillion times longer than the entire age of the universe so far. It is very nearly immortal, one of the most stable things in all of existence. Whatever the Planck scale is doing down there, it is not tearing protons apart at any rate we have managed to catch. This non-event carries real weight. It rules out the greediest theories, the ones that predicted protons should decay often enough for us to have spotted it by now. Those models made a bold bet about how the forces knit together near the Planck scale, and the stubbornly living protons collected the bet against them. Every year the tank stays quiet. The proton's proven lifetime stretches longer, and another batch of theories gets squeezed or killed. Yet the hunt goes on, because the proton might still decay, just more rarely than any experiment has been sensitive enough to catch. Physicists are building even bigger tanks, watching even more protons, reaching for even fainter signals. Somewhere out at the edge of these ultra-rare events lies a possible message from the Planck scale, a whisper about how the deepest forces come together. Catching a single proton in the act of dying would be one of the greatest discoveries in the history of science. So we chase the Planck scale in giant water tanks and in distant gamma-ray bursts. But a few daring physicists took a completely different path. Instead of watching the sky, they decided to build a small, tame copy of its strangest physics on a table in the lab. You cannot make a real black hole in a laboratory, but you can make something that behaves like one, using sound instead of light and flowing gas instead of gravity. And when physicists built one, it began to glow, exactly as the deepest theory predicted. The trick rests on a simple idea about escape. A black hole traps light because, past its edge, you would have to move faster than light to get out, which is impossible. Now picture a waterfall, and imagine fish that can only swim at a certain top speed. Near the top, where the water flows gently, a fish can swim upstream and escape. But at some point downstream, the water rushes faster than any fish can swim. Past that line, no fish can ever swim back up. It gets dragged over the edge, helpless. For the fish, that line works exactly like the edge of a black hole. Physicists build the same trap with sound. They take a gas and chill it to nearly absolute zero, so cold it becomes a strange, silent fluid. Then they make part of that fluid flow faster than the speed of sound within it. Now, sound waves get caught. In the slow region, a sound wave can travel back upstream. Past the line where the fluid outruns sound, no sound wave can escape. They have built a sonic black hole, an event horizon made of flowing gas, a place of no return for sound. Why bother with a fake black hole made of sound? Because of a famous prediction, the physicist Stephen Hawking showed that real black holes should glow. Thanks to quantum effects right at the edge, they leak a faint stream of particles over time. This Hawking glow is one of the most important predictions in physics, and we may never measure it on a real black hole, because the glow from a real one is far too faint to detect across space. The sonic black hole offers a way in. The same quantum math predicts that the sound version should glow too, leaking faint ripples of sound from its horizon, a sonic echo of Hawking's prediction. And in a landmark experiment, a physicist cooled his gas, set up the horizon, and watched. The sonic black hole glowed. Faint pairs of sound ripples came off the horizon, matching Hawking's prediction closely. Here is why this reaches all the way to the Planck scale. Hawking's glow has always carried a nagging worry. The math seems to trace the glow back to ripples smaller than the Planck length, into the region where our physics breaks down. Skeptics feared the whole prediction might secretly depend on unknown Planck scale details, making it untrustworthy. But the sonic black hole has its own smallest scale, the spacing between its atoms. its own version of a Planck length. And the glow survived anyway. It appeared, even though the tiny grain of the fluid should have ruined it. That is a precious clue. It suggests that Hawking's glow is robust, real, and trustworthy, standing firm without depending on the messy details of the smallest scale, even without a finished theory of the Planck world. A tabletop of cold gas gave physicists a rare gift, a way to test an idea born from the collision of gravity and the quantum in a place they could hold in their hands. We have chased the Planck scale through explosions, water tanks, and lab benches. Now it is time to ask the biggest question of all. Can we ever write the single theory that finally rules this hidden world? For 100 years, the smartest people alive have chased one prize above all others, a single theory that unites gravity and the quantum into one seamless whole, a theory that finally works at the Planck scale. They call it quantum gravity, and it is the holy grail of physics. We have seen why it is so desperately needed. Our two great theories, gravity and the quantum, each rule their own domain flawlessly, yet they contradict each other, and at the Planck scale, they collapse into nonsense and infinities. A true theory of quantum gravity would heal that rift. It would be one set of rules describing a falling apple and a single electron and the birth of the universe, all at once, without ever breaking down. The dream is old and personal. Even Einstein, in his final decades, poured himself into a search for a unified theory, a single framework to tie the forces of nature together. He chased it until he died, filling page after page with equations, and he never found it. The greatest mind of his age spent his last years reaching for this grail and came up empty. That is how hard the problem is. Since then, brilliant physicists have opened many roads toward it. We have met two of the boldest, one that weaves space from loops, one that builds everything from vibrating strings. There are others still, with their own strange pictures, each trying to describe the Planck world in a way that finally makes sense. Every one of them is unfinished. Everyone faces the same brutal obstacle, that we cannot run the experiments that would tell us which, if any, is right. What would a finished theory give us? Everything. It would tell us what really happens at the center of a black hole, where our current math screams. It would let us describe the first instant of the universe, lifting the veil over the Planck epoch. It would reveal what space and time truly are at the bottom, whether they are grainy or smooth, ticking or flowing, fundamental or built from something deeper. It would be the deepest map of reality ever drawn. And here is the possibility that keeps physicists awake at night. The final theory might demand that we surrender our most basic assumption of all. Space and time, the stage on which everything happens, might turn out to be secondary, emerging from something more fundamental underneath, the way the warmth of a fire emerges from the motion of countless unseen atoms. In that case, there would be no smooth space-time at the deepest level at all. Space and time would be approximations, useful illusions, dissolving into something stranger as you approach the Planck scale. That is a dizzying thought. We are so used to space and time as the bedrock of existence that imagining them as mere approximations feels almost impossible. Yet more and more clues, from black holes to holograms, point exactly that way. The Grail, when we finally grasp it, may force us to accept that the stage itself is painted scenery, and that the true drama happens somewhere we have barely begun to imagine, which carries us to the deepest question this whole journey has been building toward. If space and time might dissolve at the bottom, then what, in the end, is reality actually made of? Strip the universe down, layer by layer, past atoms, past quarks, past space, and time themselves. What is left at the very bottom? What is reality actually made of? At the Planck scale, our best guesses turned shockingly strange. For most of history, the answer felt obvious. Reality is made of stuff, of matter, tiny bits of solid substance. But this whole journey has been chipping away at that comfort. we found that most of a proton's weight comes from energy. We found that particles might be vibrations of strings or knots in a web of loops. We found that a black hole stores its secrets on a flat surface, tiled in Planck squares, piece by piece. The solid stuff keeps dissolving into something more abstract. One radical answer says the true foundation of reality is information. In this view, the deepest layer is built from pure yes or no facts, the raw bits the universe computes with, lying beneath particles and energy and even space. Every particle, every force, every scrap of space would be built out of these bits. The way a rich video game world is built out of ones and zeros. The universe, at bottom, might be something closer to a vast computation than a warehouse of stuff. The holographic pixel budget we met, counting a region's information in Planck tiles, fits this picture perfectly. Reality would be information first, and everything else second. An even bolder idea builds space itself out of a ghostly quantum link called entanglement. When two particles become entangled, they share a connection so deep that measuring one instantly tells you about the other, no matter how far apart they sit. It is one of the strangest features of the quantum world, and some physicists now suspect that these entanglement links are the very threads that stitch space together. In their picture, two regions of space sit near each other because their quantum bits are strongly entangled, and far apart because they are weakly entangled. Distance itself would be woven from entanglement. Follow that idea, and space stops being the fundamental stage. It becomes a tapestry, knitted from countless quantum threads at the Planck scale. Pull the threads, weaken the entanglement, and space itself would come apart at the seams. In this view, the smooth space you move through is a large-scale pattern in a web of quantum connections, and the Planck length is roughly the size of the individual stitches. Nobody knows which of these pictures, if any, is correct. Information, geometry, entanglement, vibrating strings, woven loops, or something no one has dreamed up yet. The honest truth is that at the very bottom, we are still guessing, groping toward an answer with mathematics as our only guide. The one thing the clues agree on is that the answer will be far stranger than solid little bits of matter. What all these ideas share is a jaw-dropping suggestion. The things we trust most completely, space, time, and solid substance, may all be surface appearances, gentle averages of a deeper reality that looks nothing like our daily world. Down at the Planck scale, the universe may be made of relationships, of information, of pure structure, dancing in a realm we can describe with equations but never visit. And that leaves us standing at the final edge, staring into the one place our science has never been able to follow, the very bottom of everything. We started with a simple square of chocolate and a childish game of cutting it in half. Now, at the end of this journey, we stand at the true bottom of that game, the smallest possible step in all of reality, and what waits there is the edge of the map itself. Think about how far we have traveled. We shrank down past atoms, past quarks, past everything solid, until we reached the Planck length, a size so small that a proton feels like an entire galaxy beside it. We watched space stop behaving like space, saw distance run backwards, and learned that trying to look closer conjures a black hole out of nothing. We found a smallest tick of time, a hottest possible heat, and a first instant of the universe sealed away forever. We met woven loops and vibrating strings, quantum foam and holograms, flickering black holes and nearly immortal protons. And through all of it, one truth kept returning. At the Planck scale, our finest science falls silent. This is the frontier, the place where every map we have ever drawn runs out of ink. Our two greatest theories collapse. Our equations spit out infinities. Our machines fall impossibly short. And even the light of the entire cosmos cannot carry us an image from the very bottom. The Planck scale is the coastline where the ocean of the unknown begins. For centuries, explorers drew maps of the world, and at the edges of what they knew, they scrawled a warning about the wildness beyond. The Planck scale is the modern version of that edge, It is written into the deepest laws of physics, marking the boundary of everything we understand. Cross it, and our knowledge simply stops. Somewhere past that line lie the answers to our biggest questions. What space really is, how the universe began, what reality is made of at rock bottom, and that line sits at a size we may never, ever reach. This edge glows with promise. It is the most exciting place in all of science. Every great leap in human understanding came from someone staring at exactly this kind of boundary and refusing to look away. The blank space on the map is where the next revolution hides. Right now, physicists around the world are throwing everything they have at this frontier, chasing the theory that will finally let us step across. And here is what makes it matter to you. The answers, hidden at the Planck scale, are the answers to where everything comes from. The atoms in your body, the ground under your feet, the light of every star you have ever seen, all of it rests on this hidden foundation, this smallest possible grain of reality. To understand the Planck scale is to read the source code of the universe, the deepest rules that make existence possible at all. It is the ultimate question of where we, and everything else, truly come from. So the chocolate bar had a bottom after all. You cannot cut forever. Far below the smallest thing your eyes will ever see, reality reaches its final step, and there it guards its greatest secrets behind a wall we have only just learned to knock on. The smallest scale in the universe holds the biggest mystery of all, and the race to reach it has only just begun. The map ends here. What comes next belongs to the explorers brave enough to sail past the edge.